Dear participants, I hope the Katrina was joined. Professor Katrina, are you able to hear my voice? Dear participants, are you able to hear my voice? Yeah. 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 Yes, 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 yes.
Okay. Hello.
Very good afternoon. Very good afternoon, Katrina.
Hello, hello. Sorry, it seems that there was a problem with the times. I was still in my lecture.
Yes, yes, yes. Sorry for the disturbance for you. I do apologize for that.
So how do I share my slides?
Yes. Presentation. The present now slide now. See, look at the bottom right. Present now.
Present now. Okay,
Yeah.
just okay. I can present the entire screen. Let's try it like this. I'll share this screen here, and I'll put this here. So can you see the slides?
Yeah, see.
Okay, let's try to put it in full screen. Can you still see the slides?
Yes, able to see.
Okay, fantastic. All sorted, I guess.
So before starting, let me give an introduction.
Thank you.
Dear participants, a warm good afternoon and a good evening to Australian participants. Still the time at 5 p.m. It is my immense pleasure to welcome you all, and I thank for that really patience for the last 30 minutes for this wonderful session. In this junction, I welcome all the participants, overseas research scholars, my faculty members, and today's speaker, Dr. Katrina from Australia.
Okay, thank you very much for the kind invitation. Today I will bring you a different talk about the impacts of artificial intelligence. You can find it a little bit of a provocative talk because it falls a little bit aside from the usual talks about and also topics about the domain. So I will speak to you on alternative mathematical tools to compute uncertainty. So the basis of artificial intelligence is to come up with ways that can simulate many faculties of human beings, namely cognition, reasoning, perception, and so on. And we usually use a very traditional mathematical framework to deal with the uncertainty that underlies all of these topics. In this talk, I will give you another view of how artificial intelligence can be modeled and what would be the implications in the future decision support systems. So let's have here a more quick motivation. So artificial intelligence, machine learning, deep learning. So AI has provided the fundamental blocks for the development of machine learning algorithms. And in the last decade, we have witnessed extremely high predictive powers in these machine learning, now called deep learning algorithms. For instance, for classification tasks, for forecasts, even to study the dynamics of the systems, always with very high accuracies. Now, the question that one asks, is this enough? Is accuracy a measure that simply determines if an algorithm is good or not, and a measure that will allow a user to trust its predictions? Well, I do not think so. And why? Because in the real world, we have bias, and these biases are expressed in data sets. Also, systems that are trained from different domains, and then you try to import those systems in different applications, that will also translate in a biased application. For instance, if I try to make a predictive algorithm like the one you have here, that tries to classify or predict breast cancer, given the texture and the size of a tumor, well, the question that we need to ask first is, what population are we representing? Does it make sense to make an algorithm, to train an algorithm with population from the north of India, and then apply this application in hospitals in the south of India? Is the same data uniformly represented across the entire country or across the entire world? And of course, the answer is no. So these algorithms, these machine learning algorithms that are usually based in local data sets, and then or very small data sets, and then are ported to different domains, they express these biases, and we cannot trust them. Moreover, many times data is hand labeled. And when we hand label data, we are already putting there our own human biases. So what I would like to express here is AI, as we have nowadays with machine learning approaches in which we just look at high accuracies, enough to come up with groundbreaking technologies? Well, it kind of depends. For instance, should we apply artificial intelligence algorithms for present sentences to determine present sentences? For instance, like in this example from the US, where we have two people that committed both prior offenses. So person A committed 2 armed robberies and 1 attempted armed robbery, and person B committed 2 minor juvenile crimes. So an algorithm that was applied in US was determining that the person on the person B on my right would have a higher risk to commit another crime than the person on my left, person A. And the truth is, person A actually committed a grand theft and person B didn't commit any other offense. And the reason for that was because the black box, the algorithm, the machine learning algorithm that was used to determine these offenses was by itself already biased towards gender and race, putting at risk people in societal groups. So machine learning algorithms, when we apply them in academia, just maximizing accuracy or precision, it's not enough when we port them to the real world. More considerations need to be taken into account, especially when we are dealing with human decision making. So how can AI be used to help us humans make better decisions, or even better, how can we get or how can we construct decision support systems that actually reflect human decision making? And by reflecting human decision making, I mean reflecting our own personal biases, our own paradoxical behaviors, and so on. So nowadays, all the AI and mathematical models that we have, they assume that, for instance, in economics, we have this notion of a rational agent. And this agent is rational because it's equipped with unlimited resources. It has unlimited time, It's assumed to have unlimited time, unlimited information, and computational power. Now the question is, are we humans really fully rational in terms of these definitions from economics, from which an entire set of mathematical concepts and formalisms were derived from? Well, the answer is no. Humans are actually very peculiar beings. We do not follow the rules of probability theory and logic. We are constantly violating these rules in decisions under uncertainty. So again, humans violate the laws of classical logic and probability in different ways. We violate them while making judgments, or even in decision making, where we violate notions such as the expected utility theory, which is widely used in artificial intelligence, in multi-agent systems, in economics, and so on. So machine learning can also not help us, because machine learning detects patterns, and humans are everything except patterns. So what can we do, or what alternatives or alternative algorithms or approaches can we bring to AI that could help us more in human decision-making under uncertainty? And to illustrate you that, I bring you here a very famous example that show how humans violate these rules. For instance, I'm not sure if you are familiar with the prisoner's dilemma, but the story very briefly is the following. We have two prisoners, P1 and P2. They have no means of communicating with each other. They committed a crime. They are put in two different cells. Again, they can't cooperate. And the police asks them either if they want to betray the other by defecting, or if they want to remain silent and cooperate. And each of these actions will bring them a certain utility. In game theory, the best action, or the Nash equilibrium, is when they defect. So the best choice should always be to defect. And that is, and you can see that in the following scenario. So when experiments were made with people, three scenarios were presented to them. They said, look, your opponent chose to defect. He betrayed you. What do you choose to do? Well, according to the utility, I also choose to defect him, because that's what brings me the highest reward. Although it's, if you are familiar with the game, you will have a notion of what these utilities are. If the opponent cooperates, if the police says, look, your opponent decided to stay silent, he's cooperating with you, what do you choose to do? Well, again, according to the prisoner's dilemma game, I get a higher utility by defecting. And there was this third scenario that was saying, well, if I don't tell you what your opponent chose, what do you prefer to choose? Well, according to logic, if when I know that my opponent defected, I chose to defect, when I know when my opponent cooperated, I also chose to defect, it should not matter if the opponent chose to defect or cooperate, because I always chose the same action. But the truth is, when this experiment is made with humans, under uncertainty, people to be more risk averse. And impressively, they broke the Nash equilibrium, they violated the Nash equilibrium, and they actually chose to cooperate. And it was not just one experiment, it was several experiments across the literature. So you can see here the deviation between the classical probability, what classical probability would predict, compared to what actually the humans did. So the humans were more cooperative under uncertainty. So this is something that, again, traditional probabilistic models or traditional AI cannot model, at least in a very simplistic way, because again, it's violating the law of total probability theory. So again, this leads us to what alternative mathematical tools can we bring to artificial intelligence that could allow us to express these human paradoxical decisions. And one of these fields is quantum cognition. Since the mathematics from classical probability theory are too limited to express human cognitive behavior, then we can come up with a more generalized theory that borrows the concepts from quantum mechanics in order to come up with a generalization and a full theory for decision making. And the difference between one and the other is basically resumed in a very simplistic way in the way we represent the events. While in classical theory, events are already predefined and are represented as sets, in quantum theory, events do not exist in a definite state until we measure them, until a decision is made. So you can see events that are modeled in vector spaces in quantum probability theory, while in set theory, while in classical probability theory, this is modeled in set theory. And there are already many problems, many approaches in the literature that try to bring these mathematics from quantum mechanics to AI, but they suffer from many problems. Namely, the models that they create cannot be generalized. They are not predictive, and they provide no interpretation of what the quantum concepts mean when transposed to a cognitive decision scenario. So there is basically no unified way or framework to try to express this bounded rationality that humans have, because again, humans are within, humans when make decisions under uncertainty, they are made with pressures of time. They are made with low information, with high levels of uncertainty, and so on. So we are always bounded in terms of rationality. So how can we provide a framework that actually can capture all of these paradoxical human decisions and come up with a new type of decision support systems for artificial intelligence? Well, that comes up with a new technology that I've been developing since 2014. I called it QUBIT, the Quantum-like Bayesian Inference Technologies. And the idea basically is the following. So the general intuition is based on the very famous double slit experiment. So for those who do not know, this experiment says the following. If we have a photon going through two slits, if I do not put any measuring device trying to understand which slit the photon or the electron is going through, the electron will behave as a wave, and it will create this interference pattern. While if I put a measuring device near each of these slits, then the electron will behave as a particle, and it will collapse to the classical probability theory that we are used to and we are familiar with. So it seems that there's here a phenomena that under uncertainty, particles behave in a different way. And when under certainty, so you can see that under uncertainty, particles behave as a wave, while under certainty, particles behave as matter, as particles, okay? So this is basically the underlying intuition. So if a decision maker is given a query, I can have several beliefs occurring in my time at the same time. So in classical theory, we usually represent mathematically that one event or one belief is taking place in one specific timestamp. In quantum theory, you can actually take advantage of this wave-particle duality and be able to represent several beliefs in a superposition state that shows them occurring at the same time in an indefinite state that can then create interference effects that can represent our own heuristics and biases. And these interference effects can basically make our beliefs deviate from the traditional calculations from classical theory. And only when we make a final decision, these interference effects and these waves that are occurring in our mind, crashing with each other, will collapse to a final decision. Okay? And a model that we are all used to, or we are very familiar in artificial intelligence and also in machine learning, is, for instance, Bayesian networks, where I can actually have events or nodes that are observed and nodes that are not observed, that are reasoned under uncertainty. So the idea of this model, of the models based on a quantum probabilistic approach, is simply this. Under uncertainty, under events, under uncertainty, we represent these waves, these events as waves. And again, these waves can crash with each other, can interfere, and the variable that I'm querying, the variable from which I need to make a decision, can suffer these interference effects and reveal a decision or that was not predicted by the traditional laws of classical probability theory. And so Qubit is a full ecosystem. We have the interpretation, we have the quantum mathematical formalisms, which are then used to redefine very traditional models in artificial intelligence. And we can then break this into the different models that are required for decision making, either models that are merely probabilistic, for instance, the quantum version of Bayesian networks, or we can come up with a quantum representation of models that try to model expected utility theories. We usually call these models in a graphical way influence diagrams. So all of this is based on the underlying layers, on the interpretation that is then mapped to the quantum mathematical formalisms, that is then mapped to the current AI Bayesian probabilistic models. And then it can be mapped to the different models that rely in these mathematical concepts. So let's speak about the interpretation. So humans, again, are bounded rational. So we usually apply rules of thumb or heuristics when we are making decisions under uncertainty. So whenever we make, and we also have here more optimal decisions, which are more for machines. We humans cannot achieve these optimalities that we have here, or if we achieve, it's very rare scenarios. So we can model within this framework the different levels of rationality, the unbounded rationality that shows the optimality, which is usually what computers do, maximizing measures, computing logical rules, compute Bayes rules, and so on. Then we have here the bounded rationality, where again I spoke about the application of heuristics, because humans cannot get these unachievable ideas. So we use heuristics to help us to deal with the uncertainty, but we still have a positive utility. Or from the moment that our heuristics are no longer favorable due to very high levels of uncertainty, then we start to become irrational, and we start to have low-performing utilities. So it's like a wave function that shows the different utilities or performances that you can get in a system. It doesn't just give you like a computer, that it's the optimal value that it could find. No, in here you can actually have a range of levels and degrees according to and performance degrees according to the uncertainty levels. So how can we map this then to the mathematical framework? Well, we can again, like we spoke, we have this notion of Bayesian networks that basically represent any decision problem as a set of random variables that are conditional dependent between each other. And variables that are not connected with each other can also express conditional independencies. So we are basically able to represent how one variable can influence another in a probabilistic way, in a compact probabilistic way, using these structures. And applications are, for instance, in medical domains. So under full uncertainty, so this network here represents a scenario in full uncertainty. And if I see a person, and I would say, well, according to my past historical values, the probability of you having a lung disease is around 2%, or the probability of the person smoking is 20%. But if I start to add evidence, and I know that, for instance, the person has a shortness in breath, and I know that this person smokes, then this information allows me to update my beliefs and allows me to say, okay, given this information, then there's a high probability of you having a lung disease. So probably we need to make some special tests, right? Now imagine, this is what classical probability tells us, and this is what we've been trusting since the initial developments of this framework. But again, just because the system says that we have a 70% probability of having a lung disease, that pretty much doesn't give us much information when the data can be biased and actually doesn't truly represent the decision problem. So the idea would be, if I apply here another mathematical framework that allows me to deal with uncertainty, probably I would come up with the different symptoms that would allow the decision maker to say, oh, wait, within this framework, I can also see that there's a high chance of having this and that. Maybe we should do an additional test to confirm. So it's a framework that is more generalized and would allow a different perspective of such classical system. So how would you do this? Well, this is how it would work. On my right side, you can see the representation of a simple classical network, while on the left side you can see the quantum representation, or what I call the quantum-like representation of this very same Bayesian network. So again, in here I represent the events as I don't know exactly what is the event. It's still uncertain. I know that it has a certain, it's described by a certain probabilistic vector that represents a wave function, but it can be anything. So I already modeled this uncertainty in these notes. And mathematically, well, I will skip this a little bit because it's not very intuitive. So basically, but the idea here is just to show how we can convert the mathematical classical formalisms into a quantum approach. So we can represent this notion of a superposition of beliefs or events by taking the full joint probability distribution and representing it as complex probability amplitudes. Again, so this would result in what we call a density operator, where you can actually see that we have here in the diagonal the classical joint entries of this matrix. We see something else. And this something else is precisely these interference effects that can occur between the events. So as you can see, it has the classical component, but it's more expressive because it can also allow us to see these alternative, less common scenarios that classical theory cannot capture. So again, classical theory and what we call the quantum interference. So And again, to perform classical inference, quantum inference compared to the classical inference, so in Bayesian network, it's basically just summing out all the variables that are not relevant for our domain. So it's just a marginalization. While in here, you actually can summarize everything to a mathematical formula that has the classical probability plus the interference effects. And these interference effects are really helpful when you try to come up with new ways to model cognitive aspects. For instance, if we define a belief space as the set of all possible beliefs that the decision maker can have from the moment that he is faced with a decision until the moment he actually makes a decision, then you do not have a single value expressing a probability like in classical probability theory, but you actually have a range of values showing how likely the person is to behave in a classical way and how likely a person is to also to commit less rational actions. So you can see here in the middle, so you see here the waves crashing. The transparent wave represents the classical probabilities. And when they crash, in the one that has the full color is the one that represents the quantum one. When they crash, you can see that the one that usually has the more paradoxical behavior tends to emerge, tends to get a higher probability. So people tend to fall, some people tend to fall in this region, which is the region where they perceive that choosing an action that is usually irrational, that's usually called irrational, they perceive it as something that will actually bring them a higher payoff, a higher utility. And again, it's a direct mapping from our interpretation here. So you have here a wave with the different levels of rationality, and you also can see these different levels of rationality also in this diagram. So again, when you ask a question, for instance, for the prisoner's dilemma again, to defect or to cooperate, this is all the belief space of the decision maker. And you can actually analyze this belief space. So again, the blue regions are the ones where the decision maker chose an action that got less reward. But again, they chose it because they perceived it to be better. And one can even see that the majority of the beliefs that the decision maker experiences can fall within the classical terms. So the red areas show the actions that are predicted by classical theory. But you can see that there are some events here that tend to follow the blue line, not the majority, but some. And the same when so when I start with the belief of defecting, and then I reason if I would like to cooperate, this is the distribution of the states. When you reverse, you get this distribution. So again, you can even try to visualize this, how the waves are crashing with each other according to the degrees of uncertainty. So the yellow component is more classical-like, and the blue component is more quantum, or showing, yeah, more quantum-like, one can say it like that. So revealing more these cognitive biases. So again, one can take advantage of these systems to try to, for instance, reduce these blue areas from the decision support system. So like that, there's less chance the persons behave in an unpredictable way. And given that these waves have a very specific pattern, that allows us to come up with functions that can actually try to predict very specific violations of classical probability theory, namely the one that is represented by the prisoner's dilemma. For instance, without using any learning algorithm, just artificial intelligence, just probabilistic reasoning, the quantum approach was actually able to predict all those initial values that I presented you that were violating the classical laws of probability theory with very low errors. So again, the yellow bar shows the quantum approach, and the blue bar shows the observed experimental results. So again, given that the waves show a very specific pattern, you can actually try to capture those patterns and try to model it mathematically in order to try to assess if we can use this to predict certain very specific scenarios in cognitive science. So again, but what I presented you so far is simply a probabilistic approach. Probabilities are still not enough to help us decide. And to make decisions, we usually use the laws of expected utility theory. But again, whoever tries to come, but again, humans violate this law of the expected utility theory. And if we try to come up with the new utility measures in the literature, we are completely crucified. It's a formula that's been on since the 40s and from which many fields have adopted and used in their decision problems. So coming up with a new one would not be the best approach. But coming up with a way to use this very same formula where we compute the probabilities in a different way, well, that can bring us a different novelty. So again, if we plot the expected utility theory in a diagram, we would have something like this. We would have a decision node that is connected to some utility, and both the decision and the utility is connected to a probability that defines a certain scenario. Well, if these probabilities are computed in a quantum fashion, it means that I will have again this propagation of waves throughout the system that can interfere. And again, you can come up with a very interesting analysis, because when we do not put the utility, you see that, for instance, the probability of a person choosing to cooperate in this scenario, it's quite big. The region is quite big. But when I start to incorporate the utilities, the area shrank, and the probability of the person committing more irrational or paradoxical decisions is reduced. So the utilities here made the person perceive less times that they would get a higher utility by choosing a less likely action. And again, you can analyze that again in the evolution of the beliefs in our belief space. You can even extract the area that that favors an utility of a less likely irrational decision. For instance, in this experiment, 13% of the decision space showed the irrational decisions, again, when the decision maker perceived that cooperating would bring them a more reward than, for instance, defecting. While again, the optimal and suboptimal decisions dominate the belief space. And again, you can see that across different experiments of the literature, always showing similar patterns. This one here that I highlighted is quite interesting because this experiment nearly didn't violate the laws of probability theory. And as you can see, the region that again favors irrational behavior is so small, which again shows that it's very close to a classical setting. And the applications of this can actually be quite good because you can apply these formalisms, for instance, in games, since you have utilities, you can apply it in games, and according to the degree of uncertainty, you can simulate more interference effects, which will either promote a more cooperative action or a more defect action, while the classical game tends always to converge to a very specific score or a very specific value. So again, it's not saying who's right or wrong, which approach is right or wrong, but it's simply saying that it's an alternative way of dealing with uncertainty. And one thing that probably you might be asking is, yes, so what is the difference, or what do we gain or lose by taking this quantum-like approach, by dealing with uncertainty in a different way? And actually, that can be pretty much summarized in this diagram. If I wanted to come up with a classical system that is able to express human paradoxical behavior, then I would have to make use of what it's called hidden variables or latent variables in order to increase the parametric space and allow me to have more parameters to model the decision problem. But in Bayesian networks, this is actually really bad, because adding extra random variables will make the full joint distribution increase exponentially large. So in a quantum-like approach, yes, you have parameters representing the wave function, but these parameters have at most the size of the full joint distribution. So it's an exponential growth versus the one that has the size of the full joint. They are both bad because, again, inference in Bayesian networks is always NP hard. But still, the quantum approach, given that it represents uncertainty in another way, and it's a more generalized theory of uncertainty, is able to provide more compactness in the models. Because again, since I'm dealing with a more generalized theory, it can capture more in the decision scenario. This is something that I'm currently working on, which is when should one try to apply a quantum-like approach to a classical one. And actually, there are actually mathematical formalisms that can allow you to investigate if a probability distribution is following a classical distribution or not. This specific function here is called the Wigner function. And it says that whenever you get negative values out of this distribution, then you are towards a non-classical scenario, which means that probably you will have more advantages modeling it using a quantum-like approach rather than using a classical approach. And again, we have the same patterns that we've seen before, always this pattern showing where these negative values, where this non-classicality is occurring in the belief space. So my dream is, well, this started in 2014 with my PhD, and the dream is to continue to extend this ecosystem, like I call it, in order to try to apply it in real world problems. So whenever I try to have some free time from teaching or admin work at university, I always try to expand a little bit one of these boxes. Either try to analyze what causal inferences would mean in such models because they are so relevant in medical diagnostic systems. What would dynamics mean in such approach when you have a system that evolves through time? And with this would allow us to study a little bit more social norms and the nature of cooperation. So one layer is built on the other, and I'm trying to come up with ways to finalize these fundamental layers from which many other models or applications can be made. So if you are a curious student and you are looking forward to do a PhD and you are interested in such concepts, feel free to send me an email because I'll be more than happy to collaborate to try to expand each of these boxes that you see in orange. So to summarize, this framework that I created is an alternative framework for artificial intelligence to deal with uncertainty in artificial intelligence. Because again, machines are very good in detecting patterns. So when we put data that is biased, it will also reflect the patterns that are in those biases. So measuring just resuming artificial intelligence and machine learning algorithms to a simple precision or a single value, I think it's no longer a right approach for machine learning. If you are not able to make an analysis that allows you to say a why, then I guess the model becomes pretty much empty and not very useful for the real world. But in my work, I try to come up with a decision-making AI that is more close to humans, that is actually can actually show different degrees of rationality and irrationality, and that is CoolBit. And of course, for very specific scenarios, one can take advantage of these patterns in the wave functions and try to say that, okay, if it falls in this region, then there's a high probability that the person is committing a violation to the sure thing principle, for instance. So probably the person is perceiving the scenario in a certain way that was not predicted when developing the system. Again, this analysis of the decision makers' cognitive space is very fruitful and very interesting. And again, it can be, well, my idea is to try to map this into real world problems and see how this belief space changes without being the scope of cognitive science and just very simple human decision experiments. Try to see how this cognitive space can be mapped, for instance, in medical decision making, where doctors are faced with high levels of uncertainty, also biases, and so on. Perhaps such a system could help them identify their own personal biases, or even identify new symptoms, or give more attention to symptoms that can lead to other diagnoses that probably in a classical approach would not be that easily perceived. And again, given that we provide a new expected, or at least an altered version of the expected utility theory, perhaps this can also help us to investigate, for instance, in markets, how companies interact with each other in a game theoretical way, where they have different utilities. Again, the way we compute the uncertainty that is influencing these utilities with this framework is different, which again can show us scenarios that in a classical setting would not be taken into consideration. So again, just to summarize, what I presented here is an alternative version of Bayesian inference, one of the most powerful mechanisms in artificial intelligence, and we extend this of course, in a more focused cognitive science perspective. So it allows us to detect different levels of rationality in the decision makers. It allows you to analyze the probabilities. It allows us to analyze the preferences with the different utilities, and so much more. So thank you very much. I'll be happy to take your questions.
Thank you very much, Dr. Katrina. Dear participants, if you want to ask any questions, you can post in chat box or you unmute your mic and ask them. And before going to the question and answer session, I would like to say about her brief biodata. She completed her bachelor degree in information system and computer engineering at University of Lisbon, Portugal. And here she acquired a strong knowledge in mathematics, algorithms, and programming languages. Subsequently, he studied her master degree in information systems and computer engineering at University of Lisbon, Portugal.
Yes.
Tell me.
So at the moment, so I'm doing all this work here in Australia now. And yes, if the student has, again, you just need basic knowledge on algebra and this, I would say a strong knowledge in probability theory, and a very curious mind. That's, in my opinion, that's all you need, because it's curiosity that drives all of this research, especially when you are when you don't want to follow the mainstream paths, like like the usual paths in artificial intelligence, machine learning. If you would like to be provocative, you need to be curious and allow your curiosity to drive you. But of course, without the necessary basis and formalisms, you cannot advance in your curiosity. So usually what I tell students is be motivated, be curious, and you need to know algebra and probability theory, because if you are curious, you will be able to put everything together quite easily. And you go and build your foundations from there.
Yes.
So again, if anyone here is a PhD, wants to do a PhD or a master's by research, they can send me an email, and we usually do a small entrance test, try to assess these fundamental these fundamental core concepts that are required for the PhD topic, and then we just continue with the process of application.
The participant can post any questions in chat box.
I know it was probably a very confusing talk for the nature, how to work on sentiment analysis. So that's actually a very interesting question, because again, it all comes down to the way of how you model this probabilistic approach that you use to compute or to make the sentiment analysis. So I'm not very into the literature of sentiment analysis, but if you use models that are based on a probabilistic framework, one line of research could be, well, what if we change the underlying probabilistic framework to deal with uncertainty in a different way? Then in that way, you can come up with a new way to assess to make this analysis that probably, again, will bring into more relevance sentiments that were before ignored or discarded by the limitations of classical probability theory. So you always think about the underlying layer. Whatever you see that uses probability, which is pretty much a lot in computer science, you can map it into such framework. And you just ask the question, what happens if I model this scenario with different laws or properties for uncertainty?
Any other